Maybe I'll take off my hat. All right, we are recording. This is lecture 9. We're going to go over chapter 6 today for fluid mechanics. Okay, so here's our agenda for today. Kind of a packed schedule, but it's going to be pretty helpful throughout the whole quarter. So announcements, midterms are still in work for grading because I got the other quizzes graded. So my goal is to, at latest, have that back to you by next Wednesday. Maybe like show thumbs, how was midterm? Is it okay? Kind of medium, not too good? Okay. So if you saw in midterm, right, I try to not be tricky, right? So manometry, I think that was pretty straightforward. That was one problem. The other two, so I think the second problem was like a Bernoulli's equation, but that wasn't something you haven't seen yet, but you should be able to apply the equations to. So I wanted to push you a little bit. And then the last two, right, I went over kind of in our review lecture. So that kind of showed, it was literally the same problems, right? So I haven't looked at them yet, but they look promising, so hopefully that wasn't too tricky. And then, right, concept questions were pretty straightforward. In a review lecture, I verbally stated what I was looking for. So for the stress part, right, or for like one of the assumptions for non-viscous flow, I was looking for the term shear stress. Okay, and I said that on the review lecture. For where the Bernoulli equation came from, I was looking mainly for you apply Newton's second law to a streamlined particle. And I said that in the review too. So those are like the key terms I'm looking for. Non-compressible flow, right, density is not changing. That's what I was looking for that. Okay, and then there was not a lot of questions, but one of the problems was that hinge door swinging, right? And you had to find the force resultant, and there was like a written portion. That written portion was just for me to kind of know that you understand what that force resultant means. So that basically means, I was asking, if you calculated your force resultant and your YR, which is the distance from the start of the hinge to the gate, what would you do on the other side of the gate to prevent it from swinging? So literally any answer like, I'm going to put a block here, or I'm going to put a bolt here or a rivet here that can handle this force, that's going to be acceptable. If you happen to just restate the force, I might look into it, but I'm just mainly looking for any solution that will stop that hinge door from swinging. Okay? Any questions about midterm stuff? Cool. Okay. Homework quizzes 1, 2, 3 are all graded. I'm going to hand back quiz 2, and at the end, I kind of made like a little rubric thing of how you got your grades, but I think I was pretty nice about it. I think the lowest was like a 7 if you took it. So I think that's pretty good. Quiz number 3, everyone did pretty good. If you saw, it was literally kind of the same as your homework problem, just different values. So that was pretty straightforward. A lot of you guys got it. That's why it was either a 50% or 100%. So I'll hand those back. So people did pretty good on 2 and 3, so I posted like the averages on those. So try to keep those. I'm gonna try to make the quizzes so they're kind of similar throughout the whole quarter. Because in my head, right, these homework quizzes, if you were to turn in homework, I would hopefully not expect anything lower than like a 80-ish% or 70 if you complete the whole homework. So that's kind of how I'm grading them. Mainly if you just show your concepts that you learned from that chapter, right? So we already did project survey and mid-quarter feedback. Like I said, at the middle of the class during break, I'll look at the project surveys. I'll assign the topics and try to make groups, and then I will go over what your project is about. I think it's pretty exciting that I did like a similar project format in grad school. So I hope you guys will enjoy that rather than having like a strict step-by-step process for a project of calculations. It's more of what your group interests, but we're still doing some calculations with the equations we learned from class. Okay, so 10-minute break, like I said, project introduction. And then whatever time we have left, you can meet with your group just so you can get names and numbers and contact. You guys probably have Discord already, but just in case. And yeah, I'm sorry I skipped that, but we're talking chapter 6 today. Any other questions? We are good. Alrighty, let's get started. So I was working on these lectures last night, and unfortunately there's no examples today. It's pretty lecture heavy. Sadly, just to be forward with you, that's what engineering is, right? So I don't know if you had Kim Gunderson for chem or chemistry teachers. There's like a stereotype that we're like the most more straightforward, boring subjects to be because it's like a lot of math. So I'll try to throw some jokes in there, but mainly it's a lot of concept heavy, just showing you the equations. And then I'm going to try to show examples on Wednesday to prep you for your homework this week and weekend. And we're not going to get through all of chapter 6 because it's pretty concept heavy because you're using differential equations and derivatives and integrals in this chapter. So whatever we do not get through, and you have a quiz next week, I will make sure to not test you on that because that's obviously the fair thing to do, right? Okay, so we'll buckle up, we'll get through this, and have some fun with the project stuff, okay? Any questions before we get started? All right, let's do it. Okay, so chapter 6, this is my intro before we get into all this concept stuff of basically calculus applied to fluid mechanics. So it's the application of differential analysis or differential equations. I subscript or use an acronym DE, so I don't have to type it out every time. And it's application of this calculus method so you understand things like how is velocity varying, right, in a section of a pipe, or how is pressure or shear stress varying on an airplane wing. So, right, a derivative, right, in calculus is essentially you're taking a limit, as it usually approaches to 0 or some kind of value. So that's kind of the idea behind this when you're using your differential equations when you apply to fluid mechanics. And you'll see the equations we go through, they all have kind of some kind of derivative in it. So we're mainly kind of assuming, this is an assumption, an infinitesimally control volume instead of a finite control volume. So we're like I said, we're taking that limit to like one small particle. General use for differential equations for fluid and motions. They kind of not, this is kind of surprising to me too when I read about it. Over the history of time, they haven't had like a general differential equation that kind of solves everything in fluid mechanics. They only have specific cases, which is what's in our textbook and what we're going to study. And it was just kind of interesting when I looked at like the history of ME subjects. Fluids is apparently pretty developed compared to the other subjects. So that was kind of interesting how they don't have this all figured out. So assumptions may vary, but we will usually assume viscous flow near boundaries. So right, if you have like a pipe, it's going to be more susceptible to the viscous forces on the shear stress applied to it compared to the middle of the fluid, right? It's basically in viscid flow, meaning there's no viscosity and no shear stress, okay? And this, it's outside the scope of the class, but I just wanted to mention it. How I mentioned this bullet point, how there's no like official differential equations that have it for every scenario of the fluids cases. There's CFD, which is computational fluid dynamics, which is your computers that do these calculations for you. So they use numerical analysis, right? So essentially, if your equation's unsolvable, right, they will just have outputs of values, and then they will just see plug and chug, I'll put this in, what's my output? And they keep solving that until they get the value that you want. So that's kind of how, if not all the DEs are solved, they use CFD to solve things. You can kind of think about it as if you do stress analysis. I don't know if you have FEA classes here. When I took my cohort here, that was unavailable, unfortunately, but I would recommend FEA if you take it. That's kind of like the FEA of fluids. I do some FEA at work, so it's, it's the modernized version. So you're learning the textbook stuff, the computer stuff you're going to learn in the future when you start working, right? Do they offer FEA electives here? No. They do. Next spring. Okay, that would be awesome to take. I think the professor that taught it in my cohort class, they taught it in UW Seattle. So I don't know if they left, but it wasn't offered for us. So, okay, so we're going to talk about velocity fields first because this kind of notation is for a lot of the equations that we're going to derive. So a lot of it today, unfortunately, is derivations. I basically boxed the equations, and if you happen, I want you to listen obviously to see where the equations come from, but if you space out, just know what the final equation is, and then the variables of what they mean, okay? Is there any, and then just so I know, because when I went to school, I was not a fan of derivations, but when I worked at the QSC and some of my other buddies, when some professors skipped the derivations, they were kind of upset or mad because they wanted to understand it too. Are there people that are a fan of derivations? Just so I know in the future, maybe I will just skip to it, and it's like, oh, backup slides. If you want to look, you can see them here. If not, here's the equation. If you're a fan and you don't want to come out, you can email me. That's okay. I kind of thought it was interesting just to know where, but I know how it is, 8:45, you're so tired, right? I don't want to see this long derivation professor's going to show. So, okay, I'll keep that in mind. This is why it's a long lecture, so the very last one I don't actually go through too much derivation. So, okay, so velocity field, it's a function of x, y, z, right, 3 dimensions, and time t. In your multivariable calculus class, this is pretty common, right? In your Calc 4, I think they call it. Yeah, Calc 4. So here's a figure in the top right, just showing what this is, right? You have your x, y, z. And to make sure your z is going in the right direction, use your right-hand rule, right? Curl your fingers to the x, y, thumb up in z. And then these values, I, j, k, that's just your unit vectors, but velocity is expressed in u, v, w. So velocity in that respective direction is a u, v, w, u, v, w. Okay, and like I said, unit vectors, that's just the magnitude and direction of one in those respective directions. Okay. Okay, acceleration fields. So from the velocity, right, we can take the derivative of velocity with respect to time to get acceleration, which you already know that from your physics class, right? And it's just a little different, right? These partial derivatives, this little backward 6, that just means in Calc 4, right, you have multiple variables in your equation, and you're going to take the derivative with respect to this bottom denominator part, right? So respect to time, if you have a function, right, with x, y, z, and t, this portion you should take the derivative with respect to x, respect to y, respect to z. And just because I tutored a lot of math, right, the way you kind of read these, whether if it's just a normal d derivative or partial derivative, the numerator is usually your function that you're taking the derivative of. Okay, so the denominator, like I said, is what you're going to take it with respect to. So sometimes you'll see something like this, derivative partial, take the derivative with respect to t. They'll just tag this on the end of your function. They just said that just means take the derivative with respect to t. Then this, the numerator says, take it with this function. And they usually have this function v here. Okay, it's like a little quick calculus 4 review. So you'll see in your homework, right, if we do this on the quiz, I'll have a velocity function for you. Maybe it's like x squared, y squared, z squared, t cubed. And then if I'm like, find the acceleration, right, you take the function, take the derivative with respect to each variable, and that's your answer. Okay, so if you split to every single axis, you have x, y, z. That's your respective equations. I'm not too sure if I'd ever ask you a specific acceleration. This is used to derive the equations of motions, which we'll study later at the end of the presentation. Okay, any questions so far? sorry, I want to keep it entertaining, but how do I make jokes about this stuff, right? It's like, so, and right, like, it's pretty cool. I don't know if people see you guys work on your stuff. Like, you guys are working pretty hard stuff, right? Calc 4 was a pretty intensive class for me. Calc 2 and 4 is my least favorite. Maybe I'll ask you guys later what's your least favorite, just for fun. So, okay. Angular motion and deformation. So we signify omega as angular velocity. So this is a derivation, right? This is going to lead to an equation later that you're going to need. This is kind of just a background information if you want to see how to get there. So there's points O, A, and B. And we essentially translate this by delta beta, which is this angle, delta alpha, which is this angle. And you'll see we have so many variables now. There's a lot more Greek letters coming. I think my old fluids professor, there was so many Greek variables, he just called everything theta. So he will just be like, okay, delta theta divided by delta theta, this is delta theta, partial derivative delta theta. So that wasn't really helpful. So I try to study on my Greek letters so I can distinguish which is which for you guys, right? Okay, so when you rotate an angle, you have B to B prime, A to A prime, and then essentially you have your U, which is your direction of your velocity, right? U is with respect to the x direction, plus the partial derivative of U with respect to y, and then times delta y. So if you do your unit analysis, you're going to come out with this, and you're going to see angular velocity in a second here. But essentially, right, these are the equations so once we rotate from point A to A prime or B to B prime. And the reason why we're like taking these partial derivatives, right, because these fluids are constantly changing, right, which is why we have these delta x's and y's. It's not like your static solid metal that doesn't change, right? So these are consistently changing, which is why we're taking derivatives and we have these dimensions, right? It depends on what you're taking part of. Okay, so it's going to end up like a derivative, right? We're taking the limit. So delta A, delta t, delta b over delta t. Sorry, beta and alpha. These are just the angles divided by the change in time. As time approaches to 0, if you find these values, tangent, right, that's just TOA, opposite over adjacent. So for example, for your alpha, you take this divided by this, and you get angle delta alpha. And you keep working that out. Algebra, you get this equation here. Okay, and then essentially, if you take the limit in this next step here, the time cancels out. So then you get just this value here for omega, which is angular velocity. This means angular velocity from O to A, right? Angular velocity from O to B is equal to the partial derivative of the velocity in the x direction, right, with respect to x. Same thing here. Partial derivative of velocity in the u direction with respect to y. I didn't box it here, but I'll edit this. This is what you want to box, this here. So omega O to A is equal to this. So essentially, if I give you on a quiz a function of something with a velocity in the x direction, you're going to find the derivative with respect to the x variable. Okay, so that's the derivation. If you need to write something down, write these bottom two. More specifically, just write this term right here. Nice and easy, right? These terms right here. Okay? All right, so angular motion and deformation. So here's just kind of a notation. If those two variables I showed you from last slide, if this is positive, which is your partial direction of, this is technically nu, Greek letter nu, not v. With respect to the x direction, that will be counterclockwise. But in the other direction, in the y direction, if it's positive, it will be clockwise. Okay? And if you basically solve, you want omega in the z direction, this is the equation that you're going to have to use right here. So these three are important to write down. You can see it's just half times the two terms we derived, the difference between the two. And then if you wanted to combine your omega in all three directions, right, you have I, j, k, x, y, z. And this is an important equation where your omega, angular velocity is omega, is half times the curl, and then velocity vector here. And I'm going to kind of show you how cross product works, right? Curl is essentially cross product of your del operator and velocity. So I think this was a lot of Calc 4 stuff. When I took Calc 4, this was really in there heavy, if you happen to remember. You'll see in a second this cross product operator. If you don't remember, you're just right. If you're taking it in your x term first, you block the first column, multiply diagonally down, and then subtract the other diagonal. If you need a review, there's quick YouTube videos out there. But here is basically what I'm talking about. That's the same equation that we had up there. So let me make sure. Okay, so the 1/2 is just part of the equation. So right, so this first term here, if you want to get your x term, you cover your x column here. You multiply these two terms, right, which becomes this, minus multiply these terms together, which is this. Okay, and the next one, and this is important. I believe when I took my FE exam, this was on there. I don't know if it was taking FE exam. You got to review this too. So cover this middle part, right? If you're taking the j direction, these two terms multiplied, right? So that becomes partial of u with respect to z.
For some reason, there's like a magic negative in the.
Right.
I forget why, but they throw in like a negative in the j direction.
Correct.
I'm not really sure why.
So they already implemented this here, so it is switched. Thank you for pointing that out. So if I were to do this, this would have been a negative sign, and this would have been a negative. So, right, it would have been this times this minus this times this, but then you put the negative back in, it flips. Z direction is the same thing. Okay, so if I ask for you in a quiz or exam, it looks like it's complicated and hard, right? But really, you're just taking derivatives. So if I give it to you, I'm not going to ask you to make a function for something, right? It's going to be, you're going to be given this this w or omega value, you'll be given this nu, you'll be given this u, and you'll have the variables and the derivatives. I'm not planning to make it difficult, right? It's not a calculus class. And if it's something like a special derivative, I will make sure we review it, or I'll let you know at the heads up if you need some kind of special derivative step to do that. So all of that being said, there is this term called a vorticity, which essentially is just twice your angular velocity to omega. And they use the term zeta, this is zeta, to define that. I always had trouble writing that guy. It's a weird one to write for Greek letters. So you can see it's essentially your omega equation up here, but without the 1/2, okay? And then I'm a big fan of, once you get your equation, what does that conceptually mean, right? You're going to be like, okay, I have this vorticity in zeta in my equation sheet, right? It just literally means twice of your angular velocity, okay? Okay, so hopefully we're getting, I know there's a lot of derivation. I think we're getting to cooler stuff that hopefully will wake you up just a little bit. So here, I even said it to you, right? What does vorticity mean? It's the fluid particles tendency to spin as they move, or in mathematical terms, it's 2 times omega. there is a term called irrotational flow. And in mathematical terms, that's when your omega, oh, I guess this is vorticity, right? Because there's no half, is equal to 0. And what does that mean conceptually, right? Because I'm a big fan. What does it mean conceptually from the equation? It's when fluid particles flow along a path without rotation, okay? So if you have a fluid particle here, you can see this little triangle. It's rotating as you're spinning. This one, the triangle is literally staying in spot as it's circulating. So irrotational, if this ever equals 0 in your equation, this is what it kind of conceptually means. Same thing here, right? If it's like looking like a parabola like this, irrotational, your particle is not rotating. Rotational is rotating kind of with the rotation. Yes?
So vorticity is the measure of how much is irrotational?
So the term irrotational is when that equals 0. So I guess it's not really, not the idea of like how close it is to 0, if that's what you're asking.
Okay, so it's more like the measure of how rotational it is.
Yeah, right, basically. So it's a good way of thinking about it, right? Because if it's 2 omega, there's only one variable in there. So the higher your omega, the higher the angular velocity. So you can think of vorticity as how high my angular velocity is. That answers your question. It's all conceptual stuff, but right in the end, you want that equation up there. Okay? Questions so far? Okay, so here's some examples I had. So I wanted to do something kind of fun. If you guys are on social media a lot, which unfortunately I am, there's this guy that does vortexes and drinks Coronas and beers. I wanted to put that in there, but I didn't think it'd be appropriate. So I got a sink instead with water. So this is a vortex, right? And the reason why we're going to talk about this because the term vorticity applies to this. So this is essentially, right, when from the upper view, you're going to see it rotating in a little bit of a circular form, and it's basically getting drained down here. That gravity is making that vortex look. And I'm pointing out now, the velocity in the middle is different from the outside. It's spinning faster in the middle, right? And the reason I point that out is you're going to see kind of a cool old video that I found of really explaining rotational and irrotational flow really good. That's how you know it's old. Come on. Let me take out the sound. So if you think of that vortex, they explain this as just a water tank rotating around its axis. So this first part, I write it out here if you ever go back into the slide. The first part shows the velocity varies directly with the radius. So that means as you go further out of your radius, the velocity is increasing, right? It's not reverse. So you can see here, this is what you would expect, right? It's just these sticks kind of rotating in your really slow moving vortex. They're rotating as this flow is rotating, which is rotational flow, right? But now, it's kind of hard to see, but this middle part is spinning a lot faster than the outside. So that is what we refer to inversely proportional. So that is basically your angular velocity is increasing in the middle, kind of like that sink that I was explaining to you, or if someone were to drink a Corona with the vortex, it's spinning faster in the middle, right? If that happens, you'll see if they put 2 sticks. The reason why they put 2 is because these are going to rotate simultaneously, so they counteract each other. You'll see these 2 matchsticks rotating. You see how it's not rotating in there? It's just following the circular vortex, but it's not rotating like the other one. So that's the term of, and you can see right in the middle, right, it starts rotating. So irrotational versus rotational flow. Right? In simple terms, it's this picture here. Okay? Right, we're doing good. Stick with me, guys. We're like halfway done. And I promise I'll hopefully get more examples in here. Yes?
You explain how it would, like, when you drink a Corona bottle, it goes faster if you put a straw in the middle of it?
Right, that's just pressure, right? You guys know that. So I unfortunately get those videos on my feed too. So it's, yeah, you'll see people do it with normal bottles too. So, right, it's just essentially it's releasing pressure. For example, if you guys ever have those big camping containers that you need to carry water if you're like off-roading or something, you'll see if you open the spout, right, sometimes the water won't come out because of the water pressure. So they have like a little hole at the top to release that pressure. So that pressure from the atmosphere is going to push that water back out, right? Some people, they'll just stab it. So, the atmospheric pressure pushes the surface and lets the water come out. So that's the same idea kind of with the straw. You're letting that pressure for that straw. That make sense? You can try it. You'll see it's faster. So, okay. It'd be kind of funny. That could be like a project topic for someone if they wanted to. And I doubt anyone put that in the survey, but that could be an option, right? So. Okay. Conservation of mass derivation. So now this is 6.2 in your book. So this is now applying our conservation of mass concepts from previous chapters into using our differential equation calculus. Okay, so I'll explain this figure in a moment, but this is basically just going to get you to an equation that we want, like I've been saying this whole lecture. So assumptions we make: the control volume is small, a stationary cubical element like this shown above. Like I said, U, V, W are velocity components in their respective x, y, z directions. And then this rho U is essentially an x component of the mass flow rate per unit area. Okay, so we start off with this cube here, right? Delta x, delta y, delta z. We have these because it's a fluid and it's changing. So the dimensions are changing. This rho is just they usually say rho in the middle because that's the center density of the particle. This is your velocities in the respective direction. And these are the equations of essentially your mass coming in and out. And you'll see in my derivation, you'll have this left face and right face, okay? So you'll see you'll have this PU, which is defined right here. And then you're subtracting this term here because, like I said, the fluid's changing. So you have your partial derivative of rho times u with respect to x, because we're in the x direction, multiplied by delta x divided by 2. Why? Because this is in the middle. That's why it's divided by 2. Delta y, delta z, that's the face that this is being applied to, the area. Okay? So same thing here now, except this is just positive because you're coming out. Okay, so here, this is just a subscript notation of the left face, which is your x minus delta x divided by 2. I explained that divided by 2. And then these I already had up here, right? I'm just moving it here. So this equation is this value with this subscript. This equation we just talked about is this value with this subscript on the right. Okay, so if we do our standard net rate of mass flow out and in equation, you just do this, right? Subtract them from each other. Algebra, this is your outcome. Okay, and then you can do this equation, we did it for the x, respectively in the y and z direction. Okay, and then your net rate of mass flow, totally, right, you can just combine them and this is your total output here, respective to x, y, and z. And it's essentially adding all three of these terms, except you're factoring out your delta x, delta y, delta z. So here is the main equation you want from that derivation. So this part is right here, and you added your rho derivative of the density with respect to time, just like your other equations that we've been using before. So that's your differential equation for conservation of mass. And I think I talk about this in the next slide, but I'll leave it up here because you're probably writing stuff down. It's kind of confusing because the textbook sometimes refers to this as the continuity equation, but it's weird because continuity equation we know as Q1 equals Q2, right? A1 V1 equals A2 V2. So if you're reading textbook, which I don't really know how many of you guys are, that's just a distinguishable difference. We're going to say continuity equation for this chapter specifically. Yes?
Are the two equations related in somewhat, like at least in like theory or?
Right, so it's just the idea of your mass flow rate in equals mass flow rate out for both. Yeah, so yes. I think they should have called it something else.
It's less of the continuity equation, more of a continuity equation then?
Yeah, you could. My English is not too good, so I don't know. But yeah, you could say that, I guess. Yeah. So if I refer to this on your exam, I'll just say conservation of mass equation. I will like to keep the continuity equation as our Q1 equals Q2. Yeah, fun fact, English is my second language. I used to have a really thick accent. I grew up here, so I got lucky, I guess. I don't know. So, okay. Okay, conservation of mass. So now, just to reference, right, we're doing this in Cartesian coordinates because I'm going to show you the polar coordinates equivalent later for your homework. So here, it's essentially this, I don't want to say this long equation, right, just summed up to here, okay? So this is your partial derivative, right, of density with respect to time. This is a del operator. I don't know if I explained that last time. It's from your Calc 4 class. That's just your partial derivative in x, y, z direction. It's just, right, this part, and that part. That's your del operator. Del, I don't know if I said it, but that's your triangle here. Often referred to as gradient. For fun, for Calc 4, I remember, not all of it, but some of it, right? That's essentially the descent of your steepness for your slope. It's a fancier term for your y equals mx plus b equation, the slope part, right? And then density, velocity, right? If I go here, this is your velocity, right? Omega vu. Okay, for steady flow, which is a lot of the times we're doing, this is assumed to 0. And if that is 0, you have your conservation of mass, nice and easier. It's just this. It's your right del operator with your velocity vector. And looks like density is out because you can kind of divide it onto the other side. And usually our fluid's not changing anyways. Okay? Or if you multiply these out, right, del operator with, right, so that's just this partial x, partial y, partial z, that's del operator. V is u, nu, and w. And yeah, and then, like I said, it's helpful to understand what this notation is, right? I explained it already. I think you guys already know because you guys took 4 calculus classes, but that's how you read these. Okay, polar coordinates. Why? There is a homework problem on this, so I wanted to give you the equation to make sure that you can solve it. So I think they talk about polar coordinates for sure in Calc 4. I don't know about Calc 2. But right, it's just different a coordinate system. Instead of having your standard x, y, z, you have your radius r and your theta angle for that radius, right? So that's like your main 2 variables for your polar coordinate system. So at point particle P, you have your z direction, which is your length around this way, vector. Your radius, which is your radius, right, for your line right here. And then v theta is the angle right here. And then these e's, they're just unit vectors in the respective direction, right? So for your theta, for your radius, for your z. Why they use e instead of I, I'm not too sure. Someone finds out, let me know. I think maybe they're just using e to show maybe it's for polar coordinates rather than Cartesian coordinates. And for anyone that reads textbooks too, it's like they don't explain everything of why they're using variables really so often. So you kind of have to, like I'm reading, I'll say, why did they call it this? They don't explain it, right? So we're just going to keep going with it. And that's just my assumption. E is just because it's polar coordinates, and I, j, k is for Cartesian. Okay, so you can kind of see how similar it is. I'm not going to derive y, but this is the equation for your conservation of mass using these polar coordinates. So, right, same thing that I've been telling you. So this r and rho are usually constants that will be given if you need them. This vr, v theta, vz, that's usually going to be a function, and you're going to find the derivative with respect to r, theta, or z. So, right, it looks complicated, but if you need to solve it, that's how you break it down. You find your function, derive with what it's respect to. If it's a constant, you can pull it out of your derivative or integral, right? In this case, it's a derivative. So simplify it, pull that out, find your function, and derive with the respectable variable. Okay, for steady compressible flow, here is a simplification. What changes? This guy is gone. For incompressible flow, you need it for homework. This is the equation you'll need. I did not circle it, but it's there. You'll see that I think that's homework problem 1. And I posted the homework already if you didn't see. That's homework 4. Quiz next week on that, by the way. I just remembered if I do anything derivative-wise, I'm going to keep it simple. If I go anything more, I'm not going to go anything more complicated than a chain rule, maybe. If you guys remember what chain rule is. But if I do, I'll make sure there's an example. You have some kind of practice for it before I put it on a quiz or exam. Just realized a typo. This should say stream function, not steam. Fix those really quick. Okay, we're doing good. Sorry, I know it's a little lecture heavy today. Just stay with me. We're like 9-ish slides away, and we're home free to the project, okay? Okay. Stream function, this is going to be on your homework. I think you have 2-3 problems. Just a heads up, I like this. It's not too difficult to understand the concepts here. So maybe if I do a quiz, it might be on the stream function thing. So yeah, I'm just saying I like this. That's what I'm saying. So you need to find, if this is what it's for, you need to find a function and differential equation that represents 2-dimensional steady incompressible flow, meaning there's 2 directions in this case, we're doing the x and y direction. So right from conservation of mass from the last slide, what's last slide? Right here, right? This is 3 directions. If we go to 2 directions, you just take 1 term out. This is reduced to 2 directions. Like I said, why I like this? If it's on your quiz or exam, this is pretty not too bad, right? It's just your u function respect to x, new function respect to y. And we're only in the xy plane. We're not in 3D here. Okay, so here's another new Greek letter for you. They use this little trident cactus-looking thing called psi. U and v, which is right your velocity in that respective direction, is related to the stream function. So this is a function of x and y. Okay? So here is kind of the figure for it. Your velocity in the v direction is negative of your psi, stream function with respect to x, X direction is your stream function with respect to y. If you remember from Calc 2, it's always like that. I can't remember the exact reason in Calculus Y, but when you're solving for something in X, it could, I guess this is for X, but this is for Y. But I guess when you're solving this, right, you'll have your function. I'll give this is your stream function, right? What is the velocity in the X direction? U. You find it with respect to Y here and respect to X there. Right. So it's kind of essentially this, but they just introduce a new Greek term, psi. Stream function in polar coordinates. So same idea as before, right? You have your radius here, you have your angle, and you have your two components, your velocity for theta and velocity in radius. So r is just your radius, your psi function, which is usually going to be given to you. If I do polar coordinates, you're going to get a function of r and theta. So it could be like r squared or psi equals r squared equals cosine theta, right? You take the derivative of cosine, that's like what, negative sine. R squared is 2r. So you take the derivative with respect to that variable. And here's the equations laid out for you. And again, what conceptually does this mean, right? Because I guess when I was a student, I guess I'd fairly say like I did good on exams and stuff. I was just so focused on getting the computations right, which is fair, right? You just want to do good on tests. But I guess as I'm teaching now, I want to make sure you guys know the idea behind it, right? It's just a two-dimensional equation, right, that represents your differential equation for the flow of your velocities for the u and v direction, which is your x and y direction. That was kind of a lot, but let me say it a little bit shorter. It's essentially just your velocities in the x and y direction into one equation. And then polar coordinates, that's it in one, same idea, but in your r and your theta coordinates there. Any questions so far? Okay. And you can see, right, sorry, I referred to it as continuity equation again. But if you plug this into your conservation of mass equation, you're going to get 0. So the reasons how these are defined in the previous slide of these equations, if you plug them back in, if you plug these back in, you're going to get 0. Right? Why? Because you can see it already, right? Like I said, these denominators, you just take the derivative of the function. You're just doing it the same, just flip-flopped. And they're going to subtract out to 0 there. Okay, so stream function, there are lines along which psi is constant are streamlines. Okay, so from chapter 3, streamlines are lines tangent to the velocity vector. So if this was your velocity vector here, right, your streamlines are going whichever way they're going for like a structure like this. It's like a bulkhead, x and y direction. This is your velocity in the x direction, u, velocity in the y direction, v. And where the streamlines plane tacked into that, that's the equation to get those velocity in those respective directions. Okay. Here's just another figure in the textbook for if you look at the streamlines for a house, right? Airflow's coming. If you have your streamlines, your velocity vector is tangent to that streamline. You can get your velocity in the x and y direction respectively from your, and keep going back to this equation here. Okay, and this you don't really need to write down or anything. This is just kind of showing more details about the stream function. So stream function along a line constant psi is the slope of the velocity vector, which I just told you. So if you have your psi here, right, you have your psi in respect to your x direction and y direction. These two terms were from the equation I showed previously, nu and u. This negative comes from the equation I plugged in earlier, right? And in respect to dx, dy, and if you assume along a line of constant psi, which is a constant velocity, right, for x and y directions equal to 0, you get this, and I guess I would actually write this equation down here. This is just solving along a constant psi. You get this, which if you solve for from here, you just add this over, and then you divide the dx with the dy. And what does that basically mean, right? That is your velocity in the y direction divided by your velocity in the x direction. That last equation there. Okay, almost done. This is where I skip a derivation because I know we'd be kind of fatigued out at the end here. So, okay, equations of motion using conservation of linear momentum. That's the chapter 6.3.2 for 9th edition, whoever's reading that. And these are going to be the equations you need for, I think, problem. It's one of the first 3 problems of your homework. You're going to see it. So these 3 I showed earlier in earlier slides, right? So this is the acceleration. We're basically trying to find your Newton's second law, F equals ma, to using our differential calculus for fluid mechanics. Okay? So these A's I showed earlier. If you need a review, they're in previous slides. That's going to substitute into these. Okay? And then your delta m is your density times your change in x, y, and z in 3D. Okay, so right-hand side is pretty straightforward, right? You just have these equations, multiply rho. So now we need to find our f's. And this is the last derivation thing that I'm probably going to kind of skim through to get our last equation we need. So your delta f, to find the force in that equation, right, there is delta s plus delta b. S is subscript for surface force, and b is for body force. So, like I said in these slides, I try my best to define every single variable so you're not lost when you're looking through these when you're studying for tests. But if there's something I'm missing, feel free to email me. So we take the assumption that we only take the body force of the weight of the element. So delta FB is just your change in mass times gravity. And then your surface forces comes from this big guy here, this figure. So you have your x, y, and z direction. So these are given just in the textbook. I guess just a heads up, you'll see in the next slide. If you have 2 subscripts like this, I think they show this in another class, I don't remember what. The first subscript is the axis that it's working off of, and the second subscript is the direction of the force it's working off of. So for example, this xx is in the x axis in the x direction. I take this is shear stress, right? So you're working off the y-axis, but your second subscript x is in the x direction. Okay? So these 2 subscripts is the direction, and then the first letter is direction, second letter is, first letter is the axis that it's going towards, and second letter is the direction. Okay, I'll just go through one of these. So sigma xx is your stress, right? If you subtract that of the change of your x with respect to the x direction, and you multiply by the delta x, right, because we're always from the center, this delta y and delta z is just the area you applied in. And that's how you get, right, stress times area is force. So these are just all forces. And if you sum these up using these axes, and I think they use some kind of Taylor expansion, you get these equations here. So I'm not going to go through that. Like I said, it's in the textbook if you want, but these are the forces summed up. That's what you get. I'm not going to ask you to derive these or anything. You get these. Okay? Don't be scared. It's just calculus. You guys are pros at this, right? It's just more equations in the x, y, and z direction. Why is it not scary, right? It's the way I tell you, right? It's just how you read these terms, okay? So these are usually, right, constants. Like I said, it's just your function derived with that respect to variable. So, I mean, once you get those, you're just if you had to solve for something like this, you're just solving derivatives after another. It's just like you're tabulating, you're keeping your check, right? I got this variable, here's a derivative, plug it into there. I have this function, this derivative, plug it into there, okay? So these are your general differential equations of motion here. And again, that came from these equations, right? Right-hand side came from delta m times this. Left-hand side came from delta fs plus delta fb, came from this. You get this. In viscid flow, right, that means shear stress is equal to 0, like I said in your midterm. These, like I told you how to read these subscripts, right? We say negative p, just so I believe you get this sign notation here. So you get this Euler's equation, which is just, if you plug these into here, you get this. And then compact form, this is essentially that, but you can see, right, this term is right here. This del P is here. Density is out here. Velocity, right, we have the UVW, partial of T here. Sorry, velocity is here. Del operator and another velocity. So, right, here's another velocity, del operator on denominator. And like I said, how you read these, again, two subscripts xx, right? So that means you're working off the x-axis in the x direction. Okay, this is important because if you try to do something up here, you need to know how these directions work. If this is x subscript y, you're following the x direction, but your force is going in the y direction, which usually means shear stress. But if you're in this scenario anyways, it won't matter because you assume your shear stresses are 0, right? Okay. We did okay on time, pretty good. Is there any questions? Like I said, sorry, that was kind of a lecture-heavy class. You can see we're like, the first part was a little bit like a warm-up with a bunch of algebra. Right now we kind of amped it up with calculus. So, but I think we'll be okay. The way I think of calculus is kind of not exactly like algebra, but it's like a board game that you have extra steps that you have, right? You have rules that you follow to do math. So if there's anything that, like I said, calculus is too difficult, I will make sure to show you first before I put it on a quiz or exam. But I would not go to the far of the extent of like past chain rule, because I guess that's what I only needed to solve calculus problems in engineering. I would know standard derivatives like, your x squared, your cosine derivative, sine derivative, tangent derivative. Those are all pretty standard, right, that you should know. Yes?
So that bottom one, the compact form, what is that like solving for? What is that equal?
So this is essentially, okay, believe it or not, it's just this, right? But this is essentially this. So the short answer to your question is Newton's second law in all three directions. And if you work it backwards, you'll see how we got back to there. Did that answer your question?
So was it density times the force of gravity?
Yep.
Minus del times, what is that? That would be
P is going to be,
minus del.
yep, pressure here, right, which is here. And then, yeah, so this is just the left-hand side here. If you do the unit analysis, it should come out to newtons. Yeah. And if they're following this notation, this left-hand side should still be your force. The right-hand side is your MA. Left-hand side here is just this, right? Right-hand side is here. If you work backwards up here, you don't assume these. You get this. Right? Your delta Fs come from here, which I explained. Your delta Fs are on this left-hand side. The right-hand sides are MA, which is from here. M times A's, F's, F equals MA, assumptions, simplified, and then even more simplified in all three directions. Okay, so G vector, right, is gravity x, y, z, del operator, partial x, partial y, partial z. And then here, density, partial derivative of velocity with respect to t, which is this. Velocity times the del operator times another velocity. So this velocity term is out here. And then these velocities are the same, by the way, right? They're just the same. It's just order of operation here. Del operator is on the denominator here. Okay, so short answer, it equals Newton's equations. Okay, that is it. And any last minute questions? We're gonna hopefully talk more fun stuff in our project. We have a good amount of time for that. Okay, I will, again, sorry it's lecture heavy. I will try to do some examples next Wednesday, but with the time constraint, I wanted to introduce the project to you so you have like 3 weeks to do it. So we'll just concepts for today, examples for Wednesday. Probably some more concepts too Wednesday, but some more examples done. Okay? Any other questions? Okay, we're gonna take a 10, 15 minute, we'll shoot for 12 minutes. We'll come back at 10:10. If you didn't fill out the survey, please do. I'm gonna try to make groups as fast as I can. And then I'll explain the project, and then you'll just talk to your group and meet each other. If there are more than one group interested in one subject, I will try to do the same subject twice, okay? Okay, go ahead, take a break. I will be here for, I can stay for questions, but I'm gonna divide groups for now, so. Aerospace.
Wow, most of the class wanted aerospace? Really? Maybe like 4 aerospace groups and 1 like HVAC group or something.
Okay, I'm thinking instead of me, I could do it, that's what I was thinking in my head, I'd just grind it out really quick and find each name and what they're associated with and figure it out that way. I think what I'm gonna do is, once everyone's back, we're just gonna be like, raise your hand of what you voted for, and then we'll sort out groups that way. That might be a lot faster, okay? And then I'll write names down that way, and then whoever's missing, I will add them afterwards. But yeah, we'll do that at 10:10, okay? Maybe since a lot of people are not here, I can walk around and hand back quizzes. Or not a lot of people are taking breaks. I'll explain the grading criteria, what I went with this quiz. But I'll hand these back. This way I can learn names too. Alex Ruiz, that Alex, right? This is your quiz 1. Alex, right? Yeah, okay. Kai is not here today, I think. I'm trying to get better at names, so maybe this will help me. Okay, Alexi, is there, right? Thank you, Alexi. Tristan. Darren. Darren's not here. Oh, Darren. Alejandro. You go by Alejandro or Alex?
I go by both.
Both? Okay, gotcha. Mikhail is not here. Okay. Ellis. Sean is on break. Sean's right there. This is Carlos here. Brian. Annie's not here. Nicole. Okay. Jesse. Martin. Anthony. Caden. Yep. Logan. Logan's not here. Logan. Saif. Saif is here. Go. Yusef's not here. Mustafa's not here. William's not here. McKinnon. Go. Roman's not here, I see. Tyler, right? Tyler. Okay, Olga. Abigail is sitting over there. Yep. Ayad. Am I pronouncing that right? Ayad, cool. Mira. Henry's over there. Okay, Jaden, thank you. If you didn't get quiz, I don't know if people came in. I think I handed them all out, but come up to me if you didn't get it. No Logan. Okay. Okay. Structural.
No wheels, and it doesn't bend back like that. It bends back like this. No wheels required. Oh, and you can't move your own chairs, so they're into that. No, they don't care. They care. No, they don't care. I brought my own chair and then it's a word. If they say something, I'd be like, dude, I actually got back issues from that chair. Can you go over to the other side? I am bringing my own chair because I can't stand it when it's
Alrighty, let's get started so we can get out of here earlier, hopefully. Okay, we're just gonna do, I'm gonna say each topic. We're gonna just raise hands. I'm gonna gauge just what the majority are here today. And then we'll go from there and divide up properly. So raise your hand if your first choice was aerospace. Oh my goodness. All right. 1, 2, 3, 4, 5. Keep them up, keep them up, keep them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Okay. We could do, sorry, one more time. Keep them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we might do 3 aerospace groups. 3 or 2. We'll see. Okay, automotive, raise your hand. Alrighty, that'll be one group. Oh, 4, we have 4. Okay, well, I'll write names in a second. HVAC, raise your hand for HVAC. Okay, awesome, that's a good group right there, HVAC. Structural people, structural engineering for like, bridges and such. All right, that might be a dud. Okay. Yep, turbo machinery, anybody? Okay, awesome. Oh, perfect, that's a group right there. Okay. Heat exchangers. Okay, that's okay. So I'll get groups written down, and then if you wanted to change last minute, you can raise your hand and we'll figure something out. Did anyone have heat exchangers? Reactors? Reactors.
The renewable. Is that the renewable one? Yeah.
Someone put other, I think, nuclear reactors. Okay, so we might combine that with heat exchangers if that's the group. Okay, so let's work backwards. Heat exchangers could be mixed with HVAC. So raise your hand for turbo machinery. There was like 4, right? Or 3? Okay, let's get Tyler, Ellis, Abby. Oh, whoops. Wrong way. Oh my goodness. I'm probably gonna spell your names wrong, but I'll fix it later. I will fix it in Canvas. Okay, that's turbo. Structural, nobody wanted. Right. It's not the same, but us stress guys at Boeing, we're called structural engineers. So if you ever want to go into Boeing, that is like a field. But you could do that in the aerospace column anyway. So, okay, so no heat exchangers or nuclear reactors. Okay, but you guys are in the same group. So if you convince Tyler you want to change, you guys, and you raise your hand too?
Yeah, I think it was the only one that's renewable. I don't know, you can put it there.
Okay, what was your name again?
Logan.
Logan. Oh, Logan, I have your quiz. Don't forget to get it later. Okay, so those four, Tyler, Ellis, Abigail, Logan. If you convince Tyler to do something that you like, let me know. But you guys talk, you four at the end, and let me know what project you decide on, okay? Okay, so no one wants structural. HVAC, they look at a good group. Okay, so that is Sean, Jesse, Tony, right? And McKinnon. Sorry, McKinnon, I'm totally gonna spell that wrong. Henry too? Okay. That's totally wrong. I'll fix it later. Okay, automotive. Okay. Mandar, right? It's gonna be wrong. I'm gonna fix it later. Carlos. Martin. Anyone else for automotive? Ayad. Right? Ayad, right? Yep. Okay. That's it for automotive. Okay. Okay, this is working out pretty good. We have 3 aerospace now. I'm trying to think if you guys can like work with specific people you want, or just I'll probably just assign it. So raise your hand for aerospace. It's quicker. There's 12, I think, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we'll do. Sorry, raise them high. I got to see so we know the numbers. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, there's more. I think there's more now. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we're going to do, raise them high. We'll do these 4 first right here. So, right, that's Tristan. You're Caleb, right? Caden. Darren, right? Alex. You guys can put your hands down. Next 4 is Saif, Nicole, Miroslav, Murmira, and we'll do Jaden, right? Jaden? Okay, I'm getting better at names slowly. Okay, Alexi, Samuel, Olga, Ryan. Okay, everyone's got a group in class at least? Okay, hopefully you got something you like. If not, you can talk to me. If you really want to switch, maybe let me know at least by Wednesday. But I'm pretty set on this. People who are gone, I will look at their vote and try to add them or make them groups. If they don't got one, they're not here. So you guys got priority, okay? So I'll pull this up again later to talk, but let's talk project first. Okay. Okay, let's do it. And I'm recording for people who are not here still. Okay, so important dates. I'm assigning it today, right? February 2nd. Presentation dates, or your presentation file due date is on the 23rd. So everyone has to get that submitted by midnight of this date. And so that gives you roughly, 3-ish weeks, right? That's pretty fair. This is not that much work, I think. So 3-ish weeks, and you don't have a quiz this week, so you have a lot more time to work on it. Presentation dates, there's going to be 2 because we have a pretty big class. So one's going to be on the 25th, one's going to be on the 4th of March. Okay, I will let you know which date you will go. If there is a group with one less member, I will for sure try to get them the later date, unless they prefer the earlier one for some reason. If your group has less people, once I assign everything, we can discuss if we want to. I don't think we'll just work, but maybe I'll just grade a little differently for the less or more people because there'll be less work. Okay, you can read through this project introduction I wrote, but what I basically wrote is, right, the goal of the project is to apply something we've learned in class, in the lectures, in the textbook. It could also be something outside that's related to fluid mechanics, but you have to cite your source. So I don't want something you randomly find on YouTube or something, right? So it needs to be cited and reliable. So yeah, something is related, and basically, like I said, you're gonna apply these equations to your topic. So I'm keeping it pretty broad. You will work in groups, so you can practice working with your peers, right? So in the real world, since like I started working, right, you're gonna be working with a group no matter what, so this is kind of practice for that. You'll work on your communication, your project management. It's important when you run projects for your future job. That's mainly what you're doing, right? You're not gonna sit around doing calculations all day unless you're a stressed guy like me sometimes. But projects are important. Presentation skills are also very important. So I learned this too, like this is just advice. You could be the smartest guy in this class that gets the highest scores, but if you're not good at talking at the interview, it won't really matter too much, right? So presenting yourself, presentation is very important. When you're in the industry, you're doing presentations on your project and work. That is so important because, like I said, you could be the smartest guy at work, does all the work, everything awesome, but if you don't present it to your bosses or leadership, no one's gonna know that you did it, right? So this is why I think this project is super important rather than having another midterm. It's preparing you guys when you start working in real life, okay? So you'll practice your presentation skills, like how to introduce yourself and the topics you are gonna present. Let's see what else is on here, blah, blah, blah. Okay, so like I said, equations are fine in class. In the textbook is great, I would prefer those. If you really wanted to look at an equation outside, just cite your source. Okay, variable project topic expected. Okay, so that's just the introduction of kind of why I'm doing this. So it's preparing you for life outside of school, but it's also learning about our topics, okay? So I wanted to make it easy, not too broad, so that you don't ask too many questions, that you're confused about things. Everybody will have a total of 13 slides. Unless you really want to add more, you can tell me and we can modify the grading, okay? So these are the grading criteria, but I'll go through each slide first. So slide 1 is your title slide. No points. I say later though that you need to have every single one of these slides or you're gonna get like a 5% deduction per each slide you miss. It's not hard though, right? Just look at the slide and put it in your presentation. So title, your names. I would put a nice cover photo just so you hook your audience, right? And like I said, this is supposed to be a fun learning project for everyone. Like I know you have your strict projects for machine design and things like that. So this is meant for everyone to learn off of each other of what they're interested in. And we can learn what we learn in class is applicable to the real world. And just as a background, I got this from my composites class analysis from UW Seattle in grad school. I think Professor Lucas Meza, he's probably there if you guys ever do grad school. He's awesome, he's like a composites expert. And we had a project similar, and everyone did research on composites and a project on it, what we learned in class. So it was arranged from like fishing pole composites to hockey stick to snowboard composites to wing composites, right? There were so many different things, and it was like when you sit down and watch the group presentation, you're not just like dying of boredom, right? It's like you're actually interested in what your classmates are learning about. So this is what it's all about for this project, okay? A little stress-free, but fun, and you're still learning. So slide 2, quick introduction of each group member, and I put that in there, right, because it's practice when you introduce yourself in interviews or presentations at work, so you don't get too nervous, right? But I used to get nervous too when I was in school, so I just keep practicing is why I put that in there. Your name, and I put why you studied ME, just because we didn't do that on the first day. I didn't want to take too much time. This is just so I get to know you guys better, and I know faces to name. And right, that's my whole spiel of the UW Bothell thing, right? We get to kind of know each other a little bit better. And I'm starting to know almost everyone's name, so that's pretty good. Slides 3 and 4, you're going to explain to the class what your project topic is. So there's 3 aerospace groups. So you're going to have to divide specifically what you want, and you have to tell the other group. And you guys have Discord and stuff, so please just communicate with that with me, or with each other, and then tell me. So one could be like airfoil, one could be jet engine fan blade, one could be aerodynamics, air efficiency, right? So you guys can do what you want within your group. So slides 3 and 4 is explaining to the class what your project is and why it's applicable to fluid mechanics. I kept these 2 slides pretty broad, like I'm not looking for specific points. I just want you to explain to the class for someone who doesn't know anything about turbo machines or someone who doesn't know anything about HVAC, start from the beginning so we can all understand together. That's the whole point of these 2 slides. And that's also something I learned in like industry, right? You'll have a wide group of engineers in the group. You'll have young guys, maybe closer to my age, middle-aged guys and old guys. If it's an older experienced guy giving the presentation, they use like so many acronyms, so many stuff that is only specific to Boeing or a company. Not everyone understands when you're like new and stuff. So I want you guys to present this in a way that's you're just explaining to a new group of members that don't know about your topic, okay? So that's gonna be 10%. I'll talk about kind of grading more once I explain all this. Slide 5 is your first equation. You're gonna have 2, okay? So it could be Bernoulli's, it could be the manometry equations, it could be pressure differences, okay? So find your equation 1. It could be what we learned, like I said, it could be in the textbook or a reliable source. You have a citations page at the very end. So you just need to cite your equation. And then you need to explain each variable in your equation. Like I said, like someone doesn't know it. So especially if you pull an equation from an outside source, you really got to explain every single variable and the units. So if I'm deducting points off of projects, if you have a number or a variable that doesn't have units, I'm instantly deducting points for that. I want you to get in a good habit, number, units, variable, units. That's going to help you in anything that you do in engineering, right? And then I want you to also put conceptually what the equation is for. Like Bernoulli's, right? It's a fluid, Newton's second law on a fluid particle, or basically an energy equation. So you'll have your variables, the equation, and then you'll explain what the equation is conceptually, like why do we have it, okay? Questions on so far? We're doing good? Okay, slide number 6. You're going to show your equation that you showed, and you're going to pick which variable you want to vary. So for example, if we have Bernoulli's equation, I want to vary the pressure, right? You're going to explain why you want to vary the pressure. Maybe you'll say, oh, maybe for an aircraft, right, in a Bernoulli's equation, there's a pressure difference from the top surface of the airfoil wing to the bottom. And you're going to, before you do your calculations, right, I won't know if you do this before or after, but you're going to write what you predict. So mathematically, you're going to kind of see like, oh, pressure increases because it's going to decrease or increase the velocity. You're going to put in here, what do you expect your varied variable is going to result into? Okay? And slide 7 is probably the most important, so I made it 10 instead of 5. You're going to show what happens when you vary that variable. So I'm mainly looking for a graph, a table, or some kind of quantitative data. So if you make a graph, it could be as pressure increase, what is the value of velocity, right? As pressure decreases, what's the value of maybe the density of your fluid, right? It's just density in there if it's not, if it's a compressible fluid. So yeah, I'm mainly looking for graphs, tables, and quantitative data. If you want something else, you can discuss that with me, and we could kind of decide from there. It could also be like a fancy figure showing what happens when you vary a variable. So pretty open, but slide 7 needs to be something quantitative, right? Something with numbers and show what happens in your variable. Okay, so slides 8, 9, and 10 is the same as slides 5, 6, 7. So it's the same thing, you're just doing it for your second equation. So I want you to do 2. Why did I do 2 equations? There's like 4 to 5 per each group, right? So I thought one equation would not be enough. So same thing. Okay, second equation. If you wanted to, if there are multiple variables in your first equation and you want to vary a different one for some good reasons, you could also do that. I think it'd be more interesting if you did 2 different equations, but if you do the same equation twice, you just list your reasons why, and then you could do it twice. But you got to vary different variables, right? Okay, there's that. Slide 11. I just want you to put something fun for the class that you learned throughout your project. So your whole group can say, these are 2 interesting ideas that we learned throughout our project related to fluid mechanics. And you can just state those in there like a fun fact kind of slide. And why I put those in, sometimes you'll be in a presentation and you'll remember random things and you'll use them at work, right? I remember in my fluids class, someone mentioned this, and that could come a long way when you're working, right? And slide 12 is just a conclusion of all your findings for the whole project. And just basically with the variables you varied and the results, and just a summary. Slide 13 is citations. Okay, so I put a note here. Slides 1, 2, and 13 don't have grade percentages because they're like either title slides, introductions, or citations. But I would still put them in or else you get a point deduction, right? Like a 5% I said. And like I said, if there's less members in a specific group, you can talk to me about changing work, like if there's too much work for a less amount of people. But I think we should be okay. I don't think this is 13 slides in 3 weeks. I think it's pretty easy, right? So that's pretty generous. And you don't need to have an external PDF for this presentation, right? This is going to be your submission for your grade. You don't have to have 2 documents, which I think is awesome, because usually I have to do 2 when I do projects. Okay, grading criteria. 60% is basically everything that adds up here. And my grading for this, right, I hated, the main reason why I kind of chose engineering too, I hate in grades where things are subjective. So writing class, right? I mean, writing is important, we gotta learn it. I just hate, I get a grade back for my writing, I got a B, but they're like, why? It's like, oh, because it just doesn't feel like an A. I was like, I love math, right? This is like, you're right or you're wrong. So I had the mindset of, if everyone can score 100, why can't you, right? If I'm gonna mark things down, it's gonna be, I don't understand something, or it could be clarified further. Okay, I'm not gonna mark you down like, oh, just because I don't feel like it's not an A, or it doesn't feel like a really good, I'm gonna state why. So one thing is like the units, right? If you're missing things. Also, right, I don't know how things are gonna go, but obviously the class is not curved, the class is not curved, we're not competing or anything, but if someone's is really good, sure, they're gonna get a better grade, but if someone's like a really low quality compared to that group, right, we're gonna have a little grade difference there, okay? So just keep it interesting for the class, right? That's what I'm just basically saying. So that's kind of like, yeah.
You mentioned like if you don't understand something, you're gonna like dock down points. Are you gonna like ask questions like to understand something during the?
Right, I'm gonna ask questions to clarify. I don't think it's also fully fair if I just say I don't understand, because I could just be not understanding myself, right? I'm not the smartest guy in the world. So I think if something is unclear, like kind of for the majority in your presentation, I will maybe ask about it. And then if you like kind of see like in your presentation, oh, yeah, I guess maybe that is unclear. Maybe you'll get like a few points knocked down. But like this grading, I hope they're not free points, but you know, this should really help your grade up if anyone didn't do good on the midterm or quizzes or anything, right? That's kind of the whole point of these. Yeah, question?
What citation format are we using?
Oh, like I told you, I'm not a writing guy, so anything that looks legit, like MLA or AAA, okay? Just if you use it somewhere, cite it, put it on the citation so we don't get in trouble, okay? Yeah.
So you mentioned the aerospace group, they have to find more like individual topics.
Correct.
Do the other groups also have to do that, find more specific topics for this?
Yeah, it still needs to be specific. So like the HVAC group, you're gonna have to do like an air conditioner, a heat exchanger, right? It can't just be HVAC. You need to have like a specific thing. For turbo machineries, you're gonna have a turbine or a turbocharger, right? So it needs to be specific for each group. It can't just be your topic and like all the other topics. It needs to be something specific. Specific example of an actual thing you use in industry to be more specific, okay? And when you guys come up with your things, you'll discuss with me anyways. So before you move forward, I'll be like, that's good, that's not good, and we'll discuss, okay? If you guys ever do research for professors though, right, don't follow what I'm doing for citations, right? You gotta follow whatever, they have to use like IEEE or something like that, so. Okay, let's hurry up here. Okay, presentations. There is a hard cutoff for 19 minutes. If you go over, I'll deduct a few points. So just practice to be under 19. I think that's pretty fair considering you have 13 slides and 3 of them are, kind of just talking introduction title slides, right? Then there will be like 4-ish minutes for Q&A. And what I'm going to do is there will be like, I think in Canvas there's like group numbers or something like that. I'll assign one group to ask a question for another group. And then that'll be one question for sure. And then everyone else who has other questions or comments, they can talk about afterwards, just so we have confirmed one question. And that kind of just shows your, your presentation, and for you and your classmates are kind of fair that everyone's participating. So I guess I also have to account because some people come late or miss classes. So if you do not tell me in 24 hours in advance that you are missing the presentation or coming late, you will get docked, okay? And only for the individual, not the group. Okay, that's not fair, right? Just for the individual. I think that's it, yeah. Right, so let me know 24 hours in advance. So audience participation, like that question I told you, and then just be here for your peers, right? Because people are gonna be here for your presentation, so it's only fair that and nice you're here for your peers when you present and when they watch. So just be here for each other. You guys are like a cohort, right? So like I said, each group will ask one group a question. Other groups can ask questions and comments as they want, and everyone's just being respectful. Should be an easy 10%, okay? And then group work grade. So I know group work's kind of difficult because sometimes one person will do more work than the other. To be quite honest with you, right, in the reality of things, there's never going to be a group project where everyone does the exact same amount of work. But I put here, like, this should be a free 10%. If there's one group member that literally is really standing out, that's not doing a lot of work, if 2 group members, at least 2, email me and tell me about them, I will deduct this 10% from them, right? But you need more than one person to vouch for you, so that's the 10 that I'm putting on there. And the reason, I hope everyone gets this 10 and everyone gets along, but the reason this is here is so that people don't slack off, basically, right? So you don't lose a 10% of your grade. And right, this project's pretty big number of your grade, so you can do the math. I forgot if this is 15 or 20% of your grade, and then you take 10% of that, right? That'll kind of add up. So that's it. We have 10 minutes. We'll let you talk to your group, meet each other, and questions. Is there any other questions for me for the project? Yep, I will pull that up.
Hello, sir. Nice to meet you. My name is right here. Dr.